Now, I will discuss the further exercise of chapter 25. Explain why sulfur dioxide is polar while carbon dioxide is not. We have to consider about the shape of molecule. Sulfur dioxide, in fact, it is V-shaped. So that's why the shape of molecules is very important. While the carbon dioxide, it is linear shape. You can see this one, oxygen, will draw the electrons towards itself. And you can see that the net force for drawing the electrons is going down. Hence, it is polar. The polarities of the polar bonds cannot cancel out each other. As a result, sulfur dioxide is polar. However, because carbon dioxide is linear shape, so the oxygen will draw the electrons to the left and the right with the same magnitude of the force. Or we can say the polarity of the polar bonds cancel out each other. As a result, carbon dioxide is non-polar. For question 2 is talking about what is the polarity, or how can we say a stuff is polar or not. Let's take a look for this one. Fine jets of water and tetrachloromethane are separately run from a burette into a beaker, as shown in the diagram below. That is, we put water and tetrachloromethane separately. What would you expect to observe when a positive charged rod is brought near to each liquid in turns? If it is water, now water, it is a polar molecule. This is polar molecule. Polar molecules means the molecules bears the delta negative and then delta positive. The delta negative part is about the oxygen, while the hydrogen will be delta positive part. If we put a positively charged glass rod here, then the water delta negative part will be attracted by the charge rod. The charge rod for positive parts. As a result, the liquid will be bent near to the charge rod. That is here. When water is going down, we find that it is no longer moving in a straight line. Instead, it bends. So we say that the liquid jet bend is path. While next one, if it is a tetrachloromethane, take a look for the tetrachloromethane for the shape of molecules. It is completely symmetrical. As a result, the polarities of the polar bonds cancel each other. As a result, it is a non-polar molecule. Non-polar molecules means there is no delta positive or delta negative. It is just the electron distribution will be evenly distributed. Hence, they will not be attracted by the charged rod. Finally, it's about the molecules, whether it is polar or not. This one, carbon monoxide, it is polar. CH3Cl, because it is not completely symmetric, so it is polar. CH2O, the electron will be withdrawn upward, and then hydrogen will give the electron as well. Upper part will be delta negative, it is polar. SiH4, you don't have to check the tables because it is symmetrical, so it is non-polar. While the final one, the most difficult one, I think, it is the one that contains the CC double bond, carbon-carbon double bond. Because chlorine draw electron, so it is polar as well, and it is not symmetric. As a result, it is polar. The final one, we have to add what is it affected if a molecule is polar. Now, take an example. Now, if it is a non-polar molecules, the non-polar molecules, their van der Waals force would be weaker than those which is the polar one, because for the polar one, it is negative and positive. They can sense each other. As a result, the attraction will be greater. As a result, van der Waals force for the polar molecules will be higher than that for the van der Waals force for the non-polar molecule. So this is based on the similar size. If they are comparable size, we can say it is having van der Waals force for the polar molecules will be higher. So in the polar molecules will be higher or greater than that for the non-polar one. So the problem is when we are talking about this, it is also involved the boiling point. The boiling point will be higher as well. That's the end of the chapter 25.